All right, in this example, we're trying to find the volume of the solid bounded above by x squared plus y squared plus z squared equals 6, and below by z equals x squared plus y squared. So let's try and actually draw this solid that we're trying to take a look at, just to get an idea of what it looks like. As we can see, we've got the below the above solid is a sphere. It's a sphere of radius square root 6. So let's draw a nice sphere here. And it's centered at the origin because it's x squared plus y squared plus z squared. So we've got some depth to this sphere. Now, taking a look at z equals x squared plus y squared, we could either try and give ourselves a couple traces, or we could just recognize from our types of solids that we learned in the past, or types of surfaces in the past, that this one is a paraboloid. So if you think about, right, when x equals 0, we've got z equals y squared, which is going to be this nice parabola right here. And same like when y is 0, we would have like z equals x squared, so we would have a parabola in the other direction as well. So we're going to have this nice kind of round paraboloid bowl shape. So if you picture what we've got, then we've got that kind of rounded paraboloid bowl, and then on top of it, it's cut off wherever this intersects. We're cut off by a domed portion of a sphere on the top of that piece. So that's our solid Q that we're looking for, would really be like this guy right here. Let's kind of try and highlight it. I could actually use a different color if we want. So we're looking at this guy right here we've got, and then he's rounded in the back. So it's a nice rounded region there. So one of the things we're going to have to think about then is, well, our z bounds are somewhat easy to spot once we just solve this one for z, right? We've got z squared is going to be 6 minus x squared minus y squared. And then as we take a look at that, what we need to do then is just take a square root. So z is plus or minus square root 6 minus x squared minus y squared. And then we have to think about which one. Well, we need that upper half hemisphere, so we want the positive. So we're going to use z equals the positive square root 6 minus x squared minus y squared. So those are our bounds for z. So that's the upper bound. That's the top of the solid. So we go to the square root 6 minus x squared minus y squared. And the lower bound is the paraboloid, so it comes from x squared plus y squared. Now what we have to try and figure out is, what does our region R look like? Where really is our region for R? If we think about where it's going to be, well, like we kind of have talked about in the past, if we were to say come directly above this solid and shine a light down, we're trying to see what's the shadow going to look like. And if we can picture it, it's going to be this whole intersection part right there is going to kind of come down and be underneath our shape down at the bottom. So what we really need to find is we need to find the intersection to find R. And by the intersection, what we really mean is we need to find the intersection of those two surfaces. So looking at those surfaces up above, well, we had x squared plus y squared plus z squared equals 6, and we had z equals x squared plus y squared. So let's take both of these and move everything to one side. So this would really look like x squared plus y squared plus z squared minus 6 equals 0, and this one would look like x squared plus y squared minus z equals 0. So then let's go ahead and take those two expressions that are both equal to 0 and set them equal to one another. So we're kind of going back to the original one just to not have to deal with the square root expressions. We're looking at the entire sphere in this instance. So setting the two expressions that are equal to 0 equal to each other, we end up with x squared plus y squared plus z squared minus 6 equals x squared plus y squared minus z. And what we're going to notice that's really nice here then is we've got a bunch of cancelings, right? We can subtract an x squared and a y squared from both sides. And then I can go ahead and move that z over to the other side. So we've got z squared plus z minus 6 equals 0. So what we can do at this point is we're really looking for then solutions in z. So we're finding what z values make these two surfaces the same. So factoring here, we're going to have z is, we'll need a positive 3 and a negative 2 equals 0. So then solving those, we get z is negative 3 and z is positive 2. Would solve that equation up above. Now, if we think about it, though, one of our surfaces was z equals x squared plus y squared, which if you think about x squared plus y squared, that's going to be greater than or equal to 0. We can see that in our paraboloid up above as well. So the z equals negative 3, we're just going to eliminate that solution because it doesn't work for the one solid. So then we're left with z equals 2. And so then to see our function that we get for our curve of intersection, we can plug that into either of our surfaces. So like if we do plug it into z equals x squared plus y squared, we're going to get 2 equals x squared plus y squared, which you'd get to the same place if you had plugged it into the sphere as well. So this is my region R. This is my curve of intersection. So if we draw that, we can see, well, it's circular. It's centered at the origin, and it has a radius of square root 2. So when we then look for our bounds for it, well, we can solve for y. And you'll notice we're going to have to do y equals a positive negative square root. So we'll go from the negative square root, and it's going to be 2 minus x squared. And we go to the positive square root, 2 minus x squared. That just comes from solving this for y, and then noticing we go from the lower hemisphere, or hemicircle to the, I guess, semicircle, to the upper semicircle. And then x goes from negative square root 2 to positive square root 2. So we've got our z bounds from up here, our y bounds, and our x bounds. So let's put all of those now into an integral. Try and keep our z bounds in the screen. So what we're going to have then is we're going to have the volume. We've got the integral. We'll do x first, negative square root 2 to square root 2. And then y, which is a function of x, so negative square root 2 minus x squared to square root 2 minus x squared. And then the z bounds, which go from x squared plus y squared to that square root of 6 minus x squared minus y squared. Remember that whole thing, we're just integrating one, and then we've got the order dz, dy, dx that we chose. Okay, so let's take a look at this integral. Taking dz, we just get a z on the inside. So we're going to have integral negative square root 2 to square root 2, negative square root 2 minus x squared to square root 2 minus x squared. And so then we're going to have z, where z is evaluated from x squared plus y squared to square root 6 minus x squared minus y squared. And then we've got dy dx. So we've got negative square root 2 to square root 2, integral of negative 2 minus x squared to 2 minus x squared. So we're going to have the square root 6 minus x squared minus y squared, and then we're going to subtract off x squared minus y squared, so we'll have minus x squared minus y squared, and this is dy dx. Okay, not the most beautiful looking integral, but probably something that we notice from it is, again, it's very circular in nature. So like if we look back at that region R, well, R was circular with radius square root 2. So if I instead switch over to polar, well, then we can see, well, R goes from, say, just 0 to square root 2, and then we can let theta swing it all the way around, a full rotation. So theta goes from 0 to 2 pi. And then on the inside, we need to sub in that we can either sub in x is r cosine theta and y is r sine theta, or we can recognize the little x squared plus y squared. So we can do r squared is x squared plus y squared. So my theta bounds are 0 to 2 pi. We've got 0 to square root 2 for r. And then we're going to have square root 6 minus r squared. Because notice it's really a negative x squared plus y squared. And then we really have minus r squared on the outside. And then remember that that whole thing needs to be r dr d theta. So then really we can distribute that r through to the different parts. So we're going to have the integral 0 to 2 pi, 0 to square root 2. We'll have r times the square root of 6 minus r squared. And let's go ahead and actually split these, so then that one can be dr d theta, and then plus, or really I guess minus, the integral 0 to 2 pi, integral 0 to square root 2, we'll have r cubed dr d theta. All right. Taking a look at that first one, we can recognize there's a composition, there's a 6 minus r squared underneath the square root. So, and then if we think about the u substitution of the inside function, we do have an r on the outside. So we would have du is negative 2r dr, and I do have r dr, so I can have negative du over 2 is that r dr. So then we can also change our bounds. So our bounds, well, r was 0, that's going to make u 6 minus 0, which is 6. And when r was square root 2, u is going to be 6 minus square root 2 squared, so 6 minus 2 is 4. So we're going to go 0 to 2 pi. We've got the square root of u, and then the r dr is going to become a negative 1/2, so let's just put that negative 1/2 in front. Du, oops, I forgot my inside integral, let's add that in there. Sorry about that. So my u integral now is from, careful, 6 is the lower bound, to 4. So then we have that negative 1/2 square root u, which I'll just go ahead and write as u to the 1/2 du d theta. Just for keeping things in line to look at the next integral, we've got the integral 0 to 2 pi. Looking at r cubed dr goes to r to the 4th over 4. And we're going to do that from 0 to square root 2. And this will just be d theta. Okay. So in this first integral then, we're going to have the integral 0 to 2 pi. So the u with a 1/2 is going to go to u to the 3/2. We increase by 1. We've got that negative 1/2 out front, and we're going to divide by 3/2, which is multiplying by 2/3. And that's going to be from 6 to 4, and we're still d theta. Over here, we've got minus 0 to 2 pi. So square root 2 to the 4th is really square root 2 squared, and then squared again, so really 2 squared, which is 4. So then we just have 4 over 4, which is 1 d theta. Over here, we've got the 2's cancel. So we've got negative 1/3 times 4 to the 3/2 plus, because it's negative 1/3, 1/3 times 6 to the 3/2. And this is all the integral from 0 to 2 pi d theta. And then over here we've got minus, the integral of 1 d theta is just theta, and that's going to be from 0 to 2 pi. All right, in this first part, notice everything on the inside there of this first integral is just a constant. We can work on cleaning it up a little bit, but then when we integrate it, it's just going to get a factor of theta. So if we think about 4 to the 3/2, it's really the square root of 4 cubed. So 2 cubed is 8. So we have negative 8/3. And then 6 to the 3/2, the square root of 6 isn't really anything nice, so we'll just leave it. So we have negative 8/3 plus 6 to the 3/2 over 3. This is all times theta, and we're going to evaluate theta from 0 to 2 pi. Looking at our second part over here where we're evaluating, we've got minus plugging in 2 pi to theta. So we've got minus 2 pi, and then really plugging in 0 just gives 0. And then in the first one as well, now when we evaluate theta, we really just evaluate at 2 pi, plugging in 0 just gives 0. So we have negative 8/3 plus 6 to the 3/2 over 3, all times 2 pi. And then we have minus a 2 pi. So if we really want to, we could factor that 2 pi out. So we could have like negative 8/3 plus 6 to the 3/2 over 3, all minus 1 times 2 pi, which we could do the negative 8/3 minus the 1, negative 8 minus 3, negative 8/3 minus 3/3 would be negative 11/3 plus 6 to the 3/2 over 3, all times 2 pi. And I'll just stop there. We could keep simplifying, but we'll leave it at that beautiful spot. So this was finding the volume between two surfaces using that triple integral.